Hey, I'm Sagar. Vivimos en una era digital en la que es difícil saber si algo es real o falso. हम एक ऐसे दौर में जी रहे हैं जहां यह तय करना मुश्किल हो गया है कि कोई वीडियो असली है या नकली. Nous vivons à une époque où il est difficile de savoir si ce que l'on voit est réel ou faux. Welcome to my talk on hacking deepfake detector at BlueHat.
Well. This was AI Sagar welcoming you to my talk on hacking deepfake image detection. Yes, that wasn't me. Just few lines of code and clever algorithms. Now imagine this. You wake up one morning, grab your phone, and see a video of yourself making wild claims, spreading rumors, or even committing to a crime you never did. The problem? You never said any of it. You never did any of it. But the world believes in what it sees. That's the power and the danger of deepfake. Okay, so in this session, we are going to basically cover into three halves. First, we are going to see how do we generate deepfakes using two sophisticated algorithms, namely encoder, decoder, and GAN-based. We are going to detect deepfakes in the next half, and we are going to hack the detector system that we have built on the second half. And while towards the end of this session, we'll try to learn and wrap up with some learnings and conclusions out of this talk. I want you to leave this room not just informed, but be equipped. Because in the world of fakes, knowing what's real is your greatest power. Okay, let me take you to a quick journey of how fast, because in order to understand why deepfake detectors are failing today, you have to understand how fast this space exploded. Back in 2014, GAN, aka Generative Adversarial Network, were introduced by Ian Goodfellow just out of a research lab and a research paper. Fast forward to 2017, some of the researchers or Reddit users started using that paper as for face swapping videos for explicit content and started spreading rumor. That's where the term deepfake was coined. And in 2018, the next year, Deepface Lab, an open source tool, hit the market. And that's where a lot of scammers started using it for deepfake fraud, causing public prominent figures to transfer or wire huge amounts for laundering purposes. To control these activities in social media platforms, some of the platforms like Facebook, Twitter, and TikTok started banning the deepfake content in order to control them. Google also rushed to build a deepfake detector called Assembler. In 2022, a more sophisticated diffusion model landed in the market. They were controllable, where you can control the quality of the deepfakes that you have generated. OpenAI launched DALL-E. By the time we speak in 2025, there are 15 million plus downloads on open source tools, and people are using it explicitly to have their own propaganda, to steer the videos in their directions and for their own means. Let me talk about two sides of deepfake, the light and the dark. On the left side, you have benign use cases, and some of them are quite impressive. Think about your aging actors appear young again, or multilingual dubbing of your favorite actors where they speak fluent Japanese or Hindi or different languages. One of my favorite is educational use cases where historical re-enhancements can be made more vivid or immersive. Forget about reading all those historical corpus of data. We can usually train them to create nice visualizations to teach it in our schools. On the right side, you have the scary, malicious ones. Think about politicians saying something they never did or committed. That's scary. Imagine transferring a huge amount using AI-assisted voice. So that's the malicious use cases. So here is a key takeaway. While the impact is real, you need to know about why deepfakes are important. So as I walk you through the next slides, both good or bad, I want you to ask, how do I tell what's real versus what's not? So here is your BlueHat meme wisdom. Just because a deepfake is funny doesn't mean it's harmless. Sure, swapping face for fun and laughs are cool, but using it to impersonate, scams, or mislead, that's not cool, and maybe even illegal. Before you hit share, pause and think, do I want to end up like this guy? So stay careful, stay kind, and enjoy responsibly. Okay, let's move to the core technicalities of the algorithm that I've built on how deepfakes are made. We'll be talking about the two core techniques, encoder, decoder, and GAN-based, of how to create deepfakes. First one is encoder, decoder. So in training phase, what happens is you have two persons, person A and person B. What encoder does is its job is to convert a high resolution image into a latent space or a simplified latent space, right? And the decoder job is to reconstruct the original image from that simplified latent space. So the encoder converts into a vector DB of a latent of a vector DB of facial expressions, your nose movements, your skin texture, and all of that. Now here is where the magic happens. In the generation phase, what you do is you mix the encoder of person A to the decoder of person 2. So what happens is the expressions and the facial tones are remaining same, but the identity is switched. Now if you see, the lady hat on the top of that image is gone, and the expression of the person is mapped to the expression of person of the lady. So that's basically encoder-decoder mechanisms. Next up is GAN. This is quite interesting. On the bottom, you have generator on the red box. Think of it as a creative AI, right? It tries to generate images, real life images, with some random input. And on the top, you have real images. Those are the authentic ones. What happens over there is you send both of the samples from generator and the real images and send it to a discriminator. So think of a discriminator as a super skeptical art critic, right? Who is on spot for fakes. So that's where discriminator tells that, hey, you have generated close to real images versus non-close to real images based on that generator and the discriminator laws. And the feedback loops keeps on retraining both of them on feature sets. Let's try to understand this a little bit more with this real-time example. How many of you have watched a series called Fuzzy on Prime Video? Okay, quite a lot of it. Quite relatable also. So your generator is Shahid Kapoor, and your discriminator is Vijay Sethupathi, right? Who is on spot for fakes. At the start, what Shahid Kapoor or generator does, it tries to print circles or pretty bad kind of realistic looking bills, right? And that's typically spotted at fake at the beginning. And the next step, in the green bill, it's getting closer, but it's still a little hard for discriminator to get fooled. And towards the end, after subsequent tries, the discriminator is able to generate a real-looking $10 or a $20 bill, which is flagged as real by the discriminator, and it's able to bypass. So again, generating deepfake is kind of a cat and a mouse game, where generator is trying to fool the detector or the discriminator, and discriminator is in hunt for catching fakes. Okay, next up is a demo. In this demo, before I play, it will walk you through a validation portal where my friend will actually try to upload his identity proof documents. And on top of that, we are trying to do a deepfake detection where we'll break the video into frames and then process that frame into our detection model to a spot for fakes. Okay, so there is a okay, anyway. So the first step is data gathering. where we have taken data sources of 6,000 samples from various sources like Forensics++, Deepfake Detection Challenge dataset, and Celeb dataset. The reason for choosing a varied set of dataset was to converge to all the regional surfaces of the faces. And the next step is pre-processing of those images that we have collected. The reason we do pre-processing is we want to focus on our model onto the region, and it should not waste time on focusing on backgrounds or noises. So that's one part of the pre-processing where we detect and crop faces. The next one is pretty impressive. We have added an LSTM plus human layer solution on top of our detection model. What it does, it checks for head pose estimation, blink detection, some imperfections on the tooth. If you have seen my original video, there were slight imperfections on the tooth of mine, because the deepfake model which I used, I deliberately tried to make it look a little imperfection so that you know that one is a deepfake. For blink detection. And even if you wonder, on my first video, the blink were quite inconsistent. When you blink, you don't know. It's highly not deliberate. So in deepfakes model, that actually blinks at every subsequent time, because that's kind of hard-coded, and they're trying to mimic the real life personas of any human. So that's on top of our deepfake model that I've built. I've added that as a personalized behavior, which tells that, hey, this one might be a deepfake and might not be a deepfake. Next up is a complete training flow. The complete training flow from data gathering to data pre-processing to sampling, we've split the data set into training and testing into 70:30 ratio. The testing data set is required because to test the robustness and the accuracy or the precision recall of our model. On the right image, you will see ResNet CNN. ResNet CNN is a second most widely used deepfake detection algorithm, which takes care of, I mean, it can be a different talk about if I go in deep in what ResNet CNN is and the architecture of it. But on the crux, it's good for detecting residual samples. And then we do an LSTM of a time series of data and add it with the human layer. So you have frames, you have blinks, and a time series data of all of it, and we compare it with the vector DB of the real person, that how it will behave. And then we do the metrics calculation of the confusion of the model to know that how it is performing. Is it good for production quality or not? That's the last step, and then we basically save it onto the disk for the prediction use case, so that we don't have to do the training step again and again. Next up is the prediction workflow. After we have the model that was trained, we load it. Whenever a user uploads a video, we just pre-process, do the same thing, like the crop the video on the face, detect if there are two faces on the video. All those kind of use cases are addressed also. And then load the training model, which was saved in the earlier step. And then we do the prediction on top of human layer solutions added to it, ResNet, and then it predicts as flags as real or fake. Now, in this step, we'll try to see how my model, how I bypass my model. There are only two attacks that I'm covering today. We'll also talk about the white box and black box attack. Black box attacks are quite cool. White box attacks, you have access to the model parameters, the weights and everything. So it's easier to craft an input which looks same with your bare eyes, but is different when you process it onto the model. I think Ram on the earlier slide talked about it in brief. I'm going to touch upon it a little bit as well. Okay, so AI researchers always come and say that my model is resilient. I've built a model that spot deepfakes or create deepfakes. But security researchers or generally AI researcher don't keep security or privacy in mind, right? And that's where his rock solid shield is bypassed by the next deepfake scandal or scam. Okay, so this is a rough slide or a very high-level slide of how do we do a deepfake detector assessment. First up is white box and black box. We are going to do black box in the next slides. But I want to talk about what white box attacks are. You have access to the complete model parameters, their weights, how they are behaving. So you can actually look into what are the inputs if I craft. It's not trained for that. Let's suppose if it is not trained for human layer solutions. Let's suppose if it's not trained for skin tones, for an example. Now, if you see the skin texture of deepfakes, they are highly inconsistent. Like there might be white patches, there might be some brownish, improper texture that the deepfake has generated. So if it is not trained with that, you can find it out with the model parameters. So that's basically not good. That's basically where you can figure out that, hey, if I craft this input, just in a vision-based system, for sure, you can do it in audio and textual deepfakes also in other modalities. But this is how white box happens. So black box, you don't have access to the model. You don't have access to anything. You just have access to the inputs that you can send and learn from the responses that you are getting from the model. Visual inconsistencies, statistical properties. So now, to the next slide. OK. OK, this one. Right. So now we are getting closer, right? We learned how do we detect, how do we generate deepfakes using encoder, decoder, and GAN. We learned about how do we detect deepfakes. And even with the bare eyes, you can look for imperfections. You can look for the blinks, inconsistencies. You can look for tooth movements. You can look for personas that does not resonate to the human touches of behaviors. Now we are getting towards how do we hack the detector that we have built, right? And the aim here is, given a video, the real or fake, our task is to adversarially modify the input video or image so that the detector misclassifies it as fake or real, or it does an incorrect prediction of the input video. So this one, again, I think Ram covered it in a very nice way of Carlini and Wenger slide, if you remember, of that paper. You generate this noise of the input image using some of the well-known algorithms like Carlini and Wenger, Jacobian. So you just have to code it up based on your input image. If it is, let's say, 32 by 32, you tell Carlini and Wenger algorithm to generate a 32 by 32 noise image sample. You do a cumulative addition of both the images. But with the bare eyes, if you see, it still looks as my image. But down on the matrix level, the matrices have changed on which the deepfake detection model was originally trained on. Now, when I pass this onto the detector, it misclassifies it as not deepfake. The reason being, the model weights are adjusted in such a way that it's not trained for the adversarial sample. So the popular remedy for this one is to make this adversarial samples as part of your training and testing data set. But that's not a final proof solution for adding adversarial example to your training and data set, because there are tons of algorithms that generate that noise. And there are tons of, and in that scenarios, we'll have a ton of data set which we can't keep our model training on. So that's a cat and a mouse game to spot or to bypass any vision-based model. You can for sure do that, the same thing in prompt-based, where you can tokenize, let's say, Sagar with a different A character, which still looks at A, but will bypass the prompt that you pass. Quite similar on the vision-based and on the textual tokenization of the prompt-based detection system. Next up is a second one. Now, if you see, what I tried to do here is based on a paper called Style Clip, or Clip originally translated into a Style Clip, which was based on Style GAN. So what it does, based on prompt, you can say that turn my hairs into white. And on the input image, it will detect where my hairs are. It will turn all of those into white. On the next one, I'll say that add lipstick to my mouth. The reason I'm doing all this is to hide the imperfections of the deepfake video that was there. If my skin texture is not good, for sure, you can do the same thing in Photoshop as well. So it's as simple as that. So when I pass this style clipped model or changed the model in the white hairs, it wrongly detected it as real. And turned my lips into pink, please. It translated the original video onto the real one and wrongly detected as real. So what it means here is you create the semantics of the video same, of the face same, the nose and the eyes at the same place. It should not be moved here and there, for sure. But you change it in a slighter way or adjust it in a slighter way that it will bypass the model or hide the imperfections that the deepfake model or the deepfake video was there in such a way that it just goes through or slips in through the detector model that we have built. Okay. In this next slide, let's talk about some of the other approaches of deepfake that are evolving. So in this slide or in this whole session, we talked about video, audio, and how do we combine both of them to generate a real-life looking synthetic data. Now I'm getting closer to a wide-known terms called synthetic data. That's all ChatGPT generated content. That's all deepfake generated content. It's all, we are living in between a synthetic data, and we are trying to draw a line between what's real versus what's not real. So I hope you guys are tagging me along with that real versus not real kind of a ask that I have earlier for you. In this slide, we covered about videos and audios. There are a couple of modern approaches as well, like biometrics. Someone can deepfake your biometrics. 3D, you can have a 3D avatar of yourself and retinize of your 3D deepfake. So we are getting a little closer towards all the physical features that we have, all of them getting synthetically generated. Okay, next up is the learning resources that I used for my research and this presentation. You feel free to take a screenshot of it or take a snap of it. Okay, with that, that was my research and an year of breaking detectors. Hope you will be leaving this room with some sort of learning to draw a line between what's real versus what's not. Thank you.